Hello friends, welcome you all in yet another series of lecture on digital electronics and microprocessor. Between the digital and analog signals, we have to get the digital signals, what are from the analog signals, differences. Then we have proceeded with the different logic gates, their integrations. Now in this lecture, we are going to see the concept of binary arithmetic processes, rules required for them, the different logic gates, and the Boolean algebra, how it is used for the simplification of Boolean expression. As a learning outcome, by attending this session, the student will able to explain and compare between the rules of binary arithmetic. Then they may able to compare between basic and the derived gates. They will also explain and apply the Boolean algebra. Binary arithmetic. So there will be the processes of addition, subtraction and multiplication which are carried out on binary numbers only, so it is called as binary arithmetic. In the addition process, when 0 will get odd with 0, it is called as 0. It will be having output as a 0, but when 0 is odd with 1 or 1 is odd with 0, it is called as 1. When 1 is added with 1, resultant will be 0 with the carry value of 1. In the binary subtraction process, when we are subtracting 0 from 0 or 1 from 1, result will be 0, but when we are subtracting 0 from 1, result is 1, and when we are having the subtraction process 1 subtracted from 0, resultant will be 1 with the borrow value of 1. Now we will turn towards the rules of binary multiplication. The binary multiplication is having rules like when 0 is multiplied with 0 or 1 is multiplied with 0 or 0 is multiplied with 1, the resultant will be 0, but here please pardon me, this 1 is multiplied with 1, resultant will be 1. Now we will go one another process involved on binary numbers, and that is nothing but the complement calculation. The complement calculation will be of r's complement and r minus 1's complement type, where r is nothing but the radix of that numbering system. So corresponding to the binary number system, the radix value is 2. So r's complement for binary will be 2's complement, and r minus 1's complement will be 1's complement itself. Similarly, for the decimal number systems, r complement will be 10's complement and r minus 1's complement will be the 9's complement value. Now, one by one we will see how to obtain these r's and r minus 1's complement, that is 1's, 2's, 9's and 10's complement values. So first we will see the procedure by which 1's complement is obtained. It's very simple. We have to replace simply the 0 value by 1 and 1 by 0 in the original given binary number. And when we will do this, we will obtain the 1's complement for that given binary number. Similarly, for obtaining the 2's complement, first we have to obtain the 1's complement number for that given number, and in that at the LSB position we have to add 1, and here binary addition we have to carry out. Next process we will see for the nines complement calculation for the given decimal number. To calculate the nines complement, we have to subtract every digit of the decimal number individually from 9, and this subtraction result of individual subtraction will give us the nines complement of the given number. Now for obtaining the tens complement, first we have to get nines complement of the given number, and then at the LSB position we have to add 1 into the nines complement of that number, and the decimal addition we have to carry. Isn't it very easy, friends? Get is having function which is written as y equal to x complement, or the comma sign as a power value will be written, which is said to be tilde also. So NOT gate is having symbol as a triangle, and in front of that triangle a bubble will be indicated. The logical function what the NOT gate is implementing is complementing its value. Let's say that input is 0 for the NOT gate, so by complementing 0, output we will get as 1. And in other case, if input is 1, output we are going to get by complementing is 0. Now we will go towards the AND gate. This AND gate will be indicated in the Boolean expression with the help of this asterisk sign. So the Boolean expression related to the AND gate will be pronounced as R is equal to X ANDed with Y. Now we will move towards the truth table of this AND gate. As we are finding that in the symbol we are having two number of inputs, and for the two number of inputs possibly four number of input combinations will be existing, and because of that this R, that is output variable, can be defined as like this. So in AND gate operations the result or output of ANDing will be 0 in any case when either both the inputs of that AND gate will be 0 or one of the input will be 0. But when both the inputs of AND gate are 1, the output will be 1. Now we will go to the next basic gate, which is termed to be OR gate. The Boolean expression for this OR gate will be pronounced as R is equal to X OR with Y. Now this is a symbol for OR gate, and we can again see here this OR gate will be having input as a X and Y. Again, as X and Y two inputs, so four possible input combination mentioned, and corresponding to those four possible input combinations the ORing output has been mentioned in the next column. So for the ORing, if 0 is ORed with 0, output will be 0. But if any of the input or both the inputs of OR gate are 1, then the output of ORing will be 1. Now these are the basic gates. We will move towards the derived gates. Let's check first the Boolean expression corresponding to these derived gates, and then we will come to the conclusion why they are said to be derived gates. Let's check the Boolean expression of XOR gate, which is written as y is equal to a complemented ANDed with B ORed with resultant of A ANDed with B complement. So you might have heard here that I have used the terms of complement, ANDing, ORing, again the value of ANDing, complementing for the variables. So I can say derived gates are the gates which are obtained from the basic gates. Here, to obtain the expression of this XOR gate, we have used the basic functionalities of complementing, ANDing and ORing. So this gate is said to be derived gate. The symbol for the XOR gate is like this. Now, for this XOR gate also, we are seeing two inputs are present. So possibly in the truth table of that XOR gate, we will have 4 output values corresponding to 4 input combinations. For the XOR gate, if 0 is XORed with 0 or 1 is XORed with 1, output will be 0, but when one of the inputs is 1, XORing output will be 1. Now we will move towards the NANDing gate. So NANDing gate can be termed as NOT AND gate. It means that first the ANDing of variables has to be carried, and that ANDing result will then complemented with the help of this bubble sign. And that's why in the expression we can see A and B has been first ANDed, and that ANDing result has got complemented. Now we will move towards the truth table of this NAND gate. In this NAND gate resultant, if both the inputs or any one of the input is 0, then NANDing resultant will be 1. But if both the inputs are 1, NANDing result will be 0. Last derived gate is the NOR gate. NOR is again to be termed as NOT OR gate. In the symbol, we can see first OR gate is present, and then in front of it again a bubble is present. That's why in the Boolean expression also we can check out it is having the value as A ORed with B, and then the resultant has got complemented or inverted. In the truth table of NOR gate, we can see that when both the inputs are 1 or any one of the input is 1, the NORing resultant will be 0, but when both the inputs are 0, NORing resultant will be 1. Now we will move towards the concept of Boolean algebra. Let me remind you friends that Boolean algebra are nothing but the simple expressions and the reduction of expression rules followed for ORing and ANDing processes. And that's why we have to see the OR rule and AND rule basically applied for the Boolean algebra. In that, first we will cover the ORing rules of the Boolean algebra. Let's take one variable as a. Now, this A will be ORed either with 0 or 1, with itself or with complement of that. So one by one, what will be the result of ORing of the A with all these 4 variables that we will check. So whenever a variable is ORed with 0, the result of ORing will be the variable itself. Now, when variable A is ORed with the variable A itself, result is also that same variable A. But when variable is ORed with 1, result is 1. The process in which the variable is ORed with the complement of that variable, resultant will be 1. Let's check this by putting the variable value of A as either 0 or 1. Let's say A is 0. So 0 ORed with 0, resultant is 0. 0 ORed with 0, resultant is 0. 0 ORed with 1, resultant is 1. 0 ORed with complement, that is 1, result will be 1. Now we will move towards the ANDing rules. In the ANDing rules, again, a one variable has to be considered, and that one variable will be ANDed either with 0, 1 with the same variable or with the complement of that variable. So results will be, if the variable is ANDed with 0, result is 0. Variable is ANDed with itself, then result is variable itself. Variable is ANDed with 1, result is the same variable. Variable is ANDed with its complement, result will be 0. Now again we will try by putting a value either as 0 or 1. Here now we will take a as 1. So 1 is ANDed with 0, result is 0. 1 is ANDed with 1, result is 1. 1 is ANDed with 1, result is 1. 1 is ANDed with 0, result is 0. Now we will see one precedence rule if we are having the two processes applied in a single Boolean expression. And in this situation, we can say that if I am having not, and or in the same expression, then the first precedence always goes to the not operation. Then next precedence comes for the ANDing operation, and finally the ORing has to be carried out. And to indicate those precedences, generally the brackets will be used or the parentheses will be used. If your original expression is A ANDed with B and C ANDed with D, and then the results of ANDing will be ORed with each other. To indicate here that AND is having more precedence as compared to the ORing, we will have the parenthesis placed for the ANDing operation, and then the parenthesis results will get ORed. Apart from this, ANDing, ORing and precedence rule, in Boolean algebra, there will be the laws which are of commutation, association, distribution and absorption types. So one by one we will cover what are those laws are going to tell us. So in the commutation law, both ANDing and ORing commutation law we have to cover. So in the ORing commutation law, we can check that if A is ORed with B, the result of it will be similar to the B ORed with A. In the same manner, if A is ANDed with B, its resultant will be same as that of B ANDed with A. In the association rule, the precedences of operation will be altered. As like for this first ORing process which is carried out is to be A ORed with B, as I am saying it is first operation because the parenthesis is placed for this operation, and parenthesis indicates the precedence value. Then this resultant will be ORed with C. Definitely the result of this whole process will be similar to when we are carrying out ORing of B and C first, and then the ORing of A will be done with the original addition resultant. In the same way, ANDing of AB and its resultant ANDing with C will have same value as that of ANDing of B and C first and then ANDed with A. Now we will move towards distribution law, in which on the parenthesis, generally the outer process will get distributed. So here in the parenthesis, first the ORing operations are mentioned, but outside the parenthesis AND is present. That means here the ANDing process is distributed over this ORing process. So let's check the resultant for distribution law. When A is ANDed and that is distributed over B ORed with C, the resultant for that will be A ANDed with B ORed with A ANDed with C. In the same way, when ORing is distributed on the ANDing operation of B ANDed with C, the OR will be distributed with variable A. Its result will be A ORed with B ANDed with A ORed with C. Now we will go towards the absorption law. In the absorption law, the variable will get absorbed. How it is absorbed, that we will check out in the next two laws. The equation is A ORed with A ANDed with C. Here absorption of C will happen and it will turn to be A ORed with A, but we have seen just here that A ORed with A resultant is A, and that's why with the help of this absorption law, the result of A ORed with A ANDed with C will be A itself. Now the next absorption law is A ANDed with A ORed with C, in which again the C will get absorbed, and finally the result of A ANDed with A, which here we have seen as A ANDed with A, is nothing but A. Now the two theorems are also present in the Boolean algebra, which are named to be De Morgan's first theorem and De Morgan's second theorem. The first De Morgan's theorem talks about the value of complementing of the variables when they will first OR, and that will be equal to their complement ANDing value. So let's check the law as when A ORed with B and its complement is taken, its value is similar to the ANDing of the complements of the two original numbers. In the same way, if we are applying ANDing and then complementing it, then it will be resultant will be similar to ORing of complementing of the two variables. How this Boolean algebra is used in the Boolean function simplification. For that, we will consider the first given equation as A ANDed with B ORed with A ANDed with B ORed with C ORed with B ANDed with B ANDed B ORed with C. So one by one, we will apply the different rules and theorems that we have seen in the last PPT for Boolean algebra. First of all, as the parentheses are present over here, the precedence we have to give for the application of these parentheses distribution law. So here A ANDing operation will be distributed on this ORing. In the same way, B ANDing operation will be distributed on this particular bracket. So the resultant will be AB, A ANDed with B distributed, then A ANDed with C will be written, then B ANDed with B and B ANDed with C. Here for second and third term we have applied the distribution law. Now we know that whenever the same variable is ANDed with the same variable, resultant is B. So by application of that rule, here the fourth term will get reduced to B. All other components will be remain same. Now in the equation we can see that this AB variable is repeated back, and we know that as ORing rule states that whenever the same variable is ORed with the same variable, resultant is a variable. So instead of writing these two separate variables, resultant of it ORing operation we are writing as a single variable, while these remaining three terms will be carried forwarded in this particular expression. The next thing we are going to do is we are going to use the absorption law, and that absorption law we are using for B ORed with B ANDed with C, where C will get absorbed and the resultant of B ORed with B is nothing but B, and the remaining two expressions are written as it is. Now again for AB and this ORing B, we will apply the rule of absorption, where this will be nothing but the absorption of A variable and resultant will be obtained as a B. So B ORed with AC is a final simplification output for this whole expression of Boolean value. Let's check one another example of simplification. So here we can see A ANDed with B complement, and that will be ANDed with C ORed with BD. Then we are having odd value of this resultant with A complement B complement, and for this whole bracket again ANDing with C will be C. As the precedences will be for the inner bracket will be first checked out, and that's why first distribution of this ANDing of A ANDed with B complement will be carried out inside this bracket. So it will result as A complement A B complement C, then ORed with A B dash BD plus this A dash B dash will be kept as it is, and outside this whole brace the ANDing by C will be written as it is. Now in this particular expression we can find out that we are having the ANDing process of a complement of a variable with the same variable. So definitely the result turns out to be 0. And now as there is ANDing of this A and D with the 0, so this whole term get reduced to 0. Now this parenthesis will be applied with the distribution law with this ANDing operation of C. So let's check. By applying this distribution law on this parenthesis, we will have resultant as A B dash C C, A dash B dash C. Now in this expression, ANDing of the same variable happens with itself, so its resultant will be the variable, that is C. Now on this particular expression, we can see that B dash C can be taken as common. So B dash C will be taken as common. So inside the bracket A and A dash will be written, and the operation of ORing will be present in between these two variables. So from the ORing rules we have seen that whenever a variable is ORed with its complement, its resultant is 1. Then we are having the rule application that variable is ANDed with 1 results into that same variable. So this long and some complex Boolean expression is simplified just as a single term as a b dash c by using the different Boolean algebra